Recording started.
In Middle System College.
In Jersey?
No, it's in Bedford, Massachusetts.
Okay.
And about 4 years ago, I had the opportunity to participate in a program in June 2008 up here, Santa Barbara, California. And in a week time, they taught us how to do microlecturing. The idea is that you can do lectures for 3 hours in a classroom. I see the faces that I consulted as kind of a white hair, so you've been in that traditional classroom that professors used to lecture for 3 hours, and I used to copy. And my language was not as excellent as some of you have that proficiency, but I used to copy and didn't understand much of the stuff that the professor wrote. And this place was, of course, MIT, and they were going fast. And I was thinking, of course, we had to dig in at night time and move on and learn the stuff, but it wasn't a very friendly and effective environment. Later, when I joined community colleges, I realized that our students have several different needs. They are not that quick, and if they are, this environment is different than many four-year colleges. So, long story short, when I went to this conference, which is done by this organization called Create, and we have a template in there, and it's well defined, the problem, the solution, and I wanted to read that by yourself. I realized that we can do things in a matter of 30 minutes rather than 3 hours. You can bring in a matter to discussion and have audience listen to that, and experience has shown that the span of attention of all human beings, especially our students, is about 30 minutes. After that, they go to the beach for So, I have chosen two different topics. First, I give you this topic, measuring the speed of light. Then I ask you to criticize, to the critics about this, and think what areas were was very good. I deliberately eliminate some good stuff and put some bad stuff in. So try to be in critical mode. Speed of light was first measured. No, you don't know it because I'm just showing at you this problem. Light is first measured in around 1671. By an astronomer called Olaf Droner. He was Swedish, I guess, by the name, and was contemporary with Luther himself. At the time when Galileo started the telescope, invented the telescope and looked at the sky, it was about 1640, early 17th century. And it was 50 years later, about that time, that only Roman, they were looking at all these planets and all. And the interesting thing about the speed of light is that most of the information we have from outer universe comes through this light, passes through the space. So it was very interesting to know the speed of light. And before that, some people have tried, say, on a far distance to create sound and then see the effect and try to compare with the speed of light, what they see or when the sound comes. And it was too fast. It couldn't do it. Because they realized that it's very fast, but they couldn't compare it with the sound that, as you know, is about 740 meters or about 2,000 feet or so. So, only Roman was looking at the sky, and you know there are planets and they go all around the sun, and specifically I am interested about this figure. Sun is at the center here, and this is the Earth that is going around the Sun. And Jupiter, which is another planet about 400 times bigger than Earth, is the fifth planet, the fourth planet. No, Mars is the fourth, Jupiter is bigger. So it's at a distance which by astronomical units, one astronomical unit is the distance of Earth and Sun. This is 1 AU, and that's about 10 astronomical units, 10 or 11 astronomical units, far from Earth or Sun. So this picture, they were looking at Jupiter, which is at point B, at this, if you can see that. And one of the moons of Jupiter called Io is going around Jupiter, that little circle. When you look at that moon of Jupiter called Io, there is a place that this moon goes behind Jupiter, and there is an X, you can't see it. Right? But when they looked at this idea of how long does it take for the moon to go behind that planet, they realized that there are different times that they are measuring. Sometimes the eclipse took 7 minutes, sometimes it took 10 minutes, sometimes it took 16 minutes, sometimes it took 23 minutes. Why is that? So that's the problem that Olaf Römer solved. That's the guts of this whole lecture. He realized that when Earth is here, at point H, it is closest to Jupiter. So when the moon goes behind Jupiter, you see the light has to travel this distance about 3h, right? And it only takes 7 minutes, right? 6 months later, the Earth is here. There's the sun, and this is the longest distance between Earth and Jupiter. So the light has to travel all this distance, right? Around here you may get 16 minutes. In here you get 23 minutes of it. In here you get 7 minutes. So, yes.
So at this time, how was it known the size of Jupiter, the distance from Jupiter, the distance?
These are not known, but they were guessed. Especially the orbit of the Sun, the size of the orbit of the Sun was not known, but it was guessed. And so that's why the first measurement seems like it within, say, 5% of accuracy. So, but it's very good, you know. So the solution came about this. He realized that at this point then it is 7 minutes, and then at this point at the other side of the diagonal it's 23 minutes. This difference is the time that light has to travel, the diameter or diagonally the orbit of Earth around the Sun. And it is 16 minutes. This difference was 16 minutes. From 7 minutes up here to 20 minutes. 23 minutes here, 16 minutes difference. And as you asked, and he somehow knew and guessed, because at that time the gravitational constant was not yet measured. It was measured later by Cavendish. And you have to know 5 generations of Cavendish people lived in Cavendish lab. So the name, years out. So this distance, as they guess, was about 93 million miles, 150 million kilometers, and the time to travel was 16 minutes or about 1,000 seconds. So when you divide, then you get something close to 300,000 kilometers per second, or 186,000 miles per second. This was the first time we guessed. Any questions?
Yeah, how did it get?
I do not exactly remember, but I can guess from the time. You know, it is an easy matter of mechanical engineering. This is how that's how by background I am a physicist too. If you equate the centrifugal force that Earth has in its rotation, and you know the annual time, so you know the period, right, for this. And you can calculate the set, because since you know the period, we have an estimate of the mass of the Earth, you can calculate. And the mass is of course cancelled. But also, they also have, by that time Newton had announced his gravitational law, which is the sun is absorbed, attracting all planets, and the two forces are equal. That's how the Earth stands. And out of that, when you cancel and simplify the equations, you get the fact that the ratio of radiuses of two planets over the period of the ratio of the period of planets is following a Rehab law. In other words, if this is the radius of the Earth, or the radius of the Jupiter, say, square, it has to do with time of Earth or the time of Jupiter. And they knew that this time for Jupiter is about 80 Earth years. So this is about 80, 1 over 80, and if you know the radius of the Earth, or somehow by I don't remember that part, but you need to have G or an estimate of gravitational constant to get to one of these ranges. And so once you have that, you can have the estimate. The general law is that F is equal to gravitational constant is m of sun divided by r squared times g. And this is m of r, right? But if you have an estimate of g, these m's cancel, and you can equate this to me omega square r of r. When you cancel this, you may get some extent. I don't exactly remember that, but they had some knowledge of that. So, any other questions? It's about 20 minutes. Cover this. Now, if I ask you this question, suppose now that after all this, you realize that the light from sun to earth takes about 8 minutes, right? How long, this is my question for you, how long does it take for the light from sun to reach Jupiter if we know that it is at 10 astronomical units? 10 times, right? So it's 8 times, that takes 8, about an hour and a half, depending on.
Oh, you need to wiggle it.
Wiggle it.
Wiggle it down. There you go.
Okay.
It doesn't like when you don't touch it.
I'm done with this. So, in this lecture, you can now judge based on a couple things. One is when I answer the subject. Question number one is that if I opened up and gave you motivation enough such that you paid attention for the next 20 minutes. Number 2 is clarity. Was it clear? Of course, create has their own training methods, and if you agree to go there and stay for a week, they'll train you for a week time. And they'll discuss all of this, and you will see a lot of 20-minute sessions working there. But along this path, I mean, if the lecture was clear, if it was conclusive, the conclusion was clear, and did you learn something? So, did we enter properly? The motivation was clear. Number 2, was the presentation clear? Number 3, the body. Two, clarity. 3, body of people. Conclusions, questions, answers.
When you say body, what do you mean?
Description. What is it? Context. Okay. Now I'll change phase and do something else. This is more technological. This is another 20 minutes of task. And now you know how you have to criticize this. This time I'm going to describe or talk about encryption and security, general computer security. So, go to this. Once I get to my computer.
What do you think?
I hope this is the best.
Your security?
No, I know which one it is. Cryptography.
And what is that?
Yes.
Here you go. It's cool.
Okay. Since 4 years ago, when we deployed some activities in class for I thought that it's not a bad idea to have a student office rather than me. So this is done by Jonathan Lamb. He's one of my best students. I also had the same talk. This is about a chapter which is about 60 pages. But I wanted to show you that you can do it in 20 minutes. Right? Keep you the lots of the whole thing in 20 minutes, and then the rest of the students were in class going through discussions, and we had a lot of discussions around this. So you can go and learn the rest of the stuff I said, rather than me even the history of this and doing the lecture as well. And in fact, one of the other students, he or she, I don't want to mention which way, this individual took about 2 hours to describe this process, and everybody was speaking. Yeah. So, Johnny Lamb did a good job. He started with little history, cryptography. You can mention the German Enigma machine around the wartime. There were all the other kinds, Greeks or Romans used to use Siberian coding, which is, if you write the 32 letters of alphabet on a circle, and in 2 concentric circles, like this. Write A here, B here, and then in the inner one, write, say A here, which is across C. Any word that you write, you can then decode. Suppose you say I am. I go with just this letter, I'm coding. Then A here changes to a C there. See that? By shifting or rotating two concentric circles. So you can go. There are other ways to go. There is a table here. This is something called Veneer cipher. You know, the motive, of course, is that everybody wants to cipher because of security. And you have a plain text called attack at down. Do you see that? And then you have a key. Key could be anything. Lemon. I only show you one of these. And that is this. You see the first word, which is A, right? And the first word in the key, which is L, coincide here. A and L. Now becomes L again. First. Next one. T and E. In this, T and E becomes X. Do you see that? So this way. And there are many ways. All I am trying to say is that if there is a key, you can type. Right? By some method. And if you move on to new encryption methods, data encryption system, DES, or the latest version of that 3DS, and American encryption, and then CAS and IDEA and Blowfish and RC. There are all different kinds of different ways that we can do this encryption symmetric. Symmetric encryption means that when you send a message, the receiver has the key, has the same exact key that you have. Right? So it's easy. The only problem with that would be the fact that if somebody, an intruder may get the key and listens to eavesdrops, and then he can decode the message or decrypt. So in symmetric encryption, as we see, you have a plain text, which is what we can read, and you send it through an encryption algorithm, and you code that, you send it through the internet or to your receiver, and they decrypt with the same key. They have it in a repository of keys, and you can always agree to have the same key by other means or by email, and you can change them too in time. However, this is I'm not going to go through all of these and read that, of course. When they introduce it to class, they start to read anything. These are all different kinds of symmetric encryption that exist. Now, asymmetric key encryption is that there is a difference between symmetric and symmetric. And the difference is that you do the same thing with the encryption, but in each side, the sender and receiver have different keys. Right? One of them, if you're familiar with security stuff, it's called BC-Hellman, one of the most simplest one. And then RSA, I don't know how we have said RSA, so encryption. But that's widely used, and they use a little bit of more sophisticated encryption techniques. The idea is that if there is an eavesdropper in the middle, since these keys differ and the eavesdropper does not have that key, he cannot decide. I'm not going into details of that, but I'm just saying that these techniques exist, And then when you use this into public domain and you want to send stuff from one side to the other side of the internet, you use this technique. Of course, encrypting all of the message is usually expensive and time. So what do you do? Suppose you have a diploma from somewhere. How do you trust that this diploma is the real diploma, like the high school diploma? What do you look at? Step, the seal, right? So why don't we do this? Electronically, we define this, we call it an electronic stick. We send the document as it is, but we only encrypt the seal, right? And that's how it is done. And if the seal is the right seal, and we trust that the sender is real sender and he has sent it, then we trust the seal, right? So this is a good picture that in this picture, I don't know if you can follow the mouse here. Can you see the mouse movement? This is the message that we are sending, right? This is the message that we are sending. We don't do anything about that. So we don't encrypt, right? But only the seal part we encrypt, right? And then we use the same technique of public key infrastructure that is asymmetric. So nobody can, in the middle, decipher this, right? And the receiver will receive that, and he will compare it with a signature that you sent, and it was not ciphered. But he also has a ciphering mechanism at his disposal. He compared the two seals. I repeat. You send the message and touch. You send the seal and touch. Should I trust that? You cipher that. And you cipher it at destination too. Cipher only the seal and baby. Computers can do that. And quickly you can say, oh, the signature or electronic signature is right. Any questions? Did we take you all the way down to encryption? Yes, sir.
So people can understand the message, but they accept it.
If
But they
the
can't.
message is a diploma,
You'll be aware of it.
if the message is a diploma, who cares? It's your diploma, right? But if the message is a common information, scientific information, it's a dangling, then you start the algorithm. You encrypt you've known probably TLS is one way that the cipher is doing banking, your check or your accounts. You never send any number to the internet and cipher. Yes.
I'm unclear how you can start out with, you end up with a public key
Okay.
and then
Then I refer you to the cannot change that in. Do that if you want to. You want to? I just want to.
I don't know.
All right, okay. All right. One thing is, in order, you have to know a little math, I'm sure you know a lot of math. An operation called mod, MOD, means that you divide two numbers and take the remainder. So if I'm teaching, funny that they're all teachers. Let me try it. Because for myself, so for anybody who is listening, this is important. One of the most important things is like a preacher when he goes to a session, is to look at the face of people, who they are, what kind of students they are sitting there, what is their background, who are the classes, and then maybe go and practice the daily lecture for 20 minutes to know how to tailor it. Very important to understand your audience. So we assume that you're like kindergarten level, and we say, hi, kids, there is an operation that we will learn later, it's called division, and if you divide two numbers, say A divided by B, you will get a quotient, which is the result of this, and the remainder, which is remainder. So the example would be 13 divided by 4, which will be 3, that's the quotient, and remainder will be 1. Right? If I say 13 mod 4, it is equal to 1. I put it equal to the remainder. Alright? So, in this example that we are going to find, let me see time, I take you, if you have computers, you can go to a place called Diffie-Hellman. Let me see if I can find it here. Going to internet, to Wikipedia, see how successful we could be.
Fine. You can use it over here.
What should I do?
Okay, you're good.
I'm good. Okay, no, in fact, I need to go to internet. Okay, let's go here. Okay. Okay. If we that's good. Okay. Diffie is a fellow at Sun Microsystems, and Professor Hellman teaches at Stanford University. So these two together put a method together that the best way to show that is shown in this picture, and then we may go to a numerical example. So Alex on one side and Bob on the other side trying to pass information. Right? We want to do something that nobody in the middle called, say, Eve, and on Eve. Right? Sometimes these things. Okay. Let me see. According to this table, see the table up there? And I hope that I can expand on the stuff that we cannot see. They have to choose some numbers on each side. And some of these would be public information, some of this would be private. Okay? The table says Alice, on her side, uses a prime number. You know, all of you know prime numbers are just divisible by themselves and by 1. Right? So 17 is a prime number. 17 is a prime number. 91 is not. Divisible by 7 and 13. 97 is a prime number. I guess 1001 might be a prime number. So, they choose a prime number. Alice chooses a prime number. In this case, she chooses this prime number to be 23. Okay? And she also chooses a number called a generator G. In this case, it is 5. Randomly. But prime number is also random, right? But it is a prime number. Then she sends these two numbers to Bob across the internet. So everybody can see them, right? So Bob also has this two pieces of information. So Alice had this, Bob also has P and G. Now, these secretly choose the private key. Alice chooses the private key A equal to 6, and Bob chooses a private key B equal to 15, right? Then on each side, they calculate two new numbers. On Alice's side, Alice calculates capital A, which is G to the power A mod P. G to the power A mod P. So if I put numbers there, it would be 5 to the power 6 mod 23, right? And once you do that with calculator, you see that this number is 8. This becomes 8. Okay? On this side, Bob does a similar thing. G to the power B mod 23. And you see that? And in this case, it becomes 19. Alright? Now they crisscross. Alice sends 8 to Bob. Bob sends 19 to Alice. They redo his calculations. In other words, Alice calculates a key G. I want to show that these two keys on both sides are the same. He uses this number 19, right? And he uses 23 and uses the mod again. So he uses 19 to the power 6 that was there, mod 23. Calculation shows that this is 2. Alright? Bob uses 8 to the power 15 that he has, mod 23. Calculation shows that this is also 2. The guy in the middle, the lady in the middle cannot know, because he doesn't have A and B. He doesn't have this and that. Right? But mathematics shows that the two keys that are present on both sides, so it goes public and private, the same, nobody can know. Now, we can now come up with some more difficult thing like RSA, rather than using mod, using a polynomial of some kind, or a log. That's how RSA is based. Any questions? See, what we have done in this class of security state is that we have broken, we have tried to break every session into 20 minutes like this. Right? I give you 3 of them today, right? And you see the students playing, rather than if you just talk about something. And you can get them involved, rather than me doing this. So you know there was no time. You can have them get their own, say, prime number, get their own ALD, and go on, and then get them involved. And so, there's 20 minutes of microlecturing going on. Okay.
Well, that was part of my question, how you usually follow up your 20-minute lecture.
But the results we have some people like Jonathan Ladd. We have people who come here and read through and don't look back. And that's not, and of course, I have always asked them to do their homework at night and be prepared for the kind of matter or material they're trying to talk about. Mostly, I would say, in 65% of the time, we have been successful. In all the other times, some people don't get it, they go for 2 hours of lecturing, they get tired, or they put something here and read, and that's not. Want the material be part of very well, be compressed into 20 minutes. What Jonathan Lamb did was a chapter of about 50 pages, but he concentrated on the important, and that's what that's the difficulty of teaching. You have to go and I would say put yourself.
The class was given an hour, let's say a 50-minute segment, or so if you have a 50-minute segment and to think things in 20-minute lecture, what do you do to students the rest of it?
Hands-on material.
Hands-on
Yeah.
material.
Most of it is opposite. For example, I introduced this to them and I asked them to very carefully. Or most of the time, the lecture goes into the lab. Right? They're not in the kitchen, they're hiding. And 20 minutes of that for grade rotations, 2 trainings, and then the rest is
Really? But you spend usually only 20 minutes for that whole
I
hour
don't
and a
speak
half?
much. I'm not that good.
Do your students read? Do they read your book?
If they don't, they can't pass the test. Because there are certain things in the chapter, there are questions, review questions, multiple choice questions they have to do. But the idea is that they give them quickly in 20 minutes before they go to sleep. And the whole picture from a vantage point. And then, yes.
Do you give a grade after the 20 minutes?
After about 5 minutes.
You get how many grades?
Then it goes to hands-on. There are lots of labs.
So I like what you say involving the students when you lecture. Do you ever run into the case where you're lecturing something and they just can't get involved? In other words, it's too complex for them to be involved and just keep going on? Have you ever challenged them?
I remember my MIT time, and I used to get bored myself. I never do more than 20 minutes of lecture. And within that 20 minutes, at a each side, I try to get them to watch. I don't think I have to. My lectures are short.
I understand, but what if it's something you're lecturing and you're involving them? You give them a concept and nobody can get involved, nobody can guess it. Then do you take the time to explain it to pull them back in? Do you understand what I'm asking?
If I'm talking about, say, measuring speed of light, you can always ask them, what's the distance, what is that, what is this, and talking about the law that generally asking, you can always get them involved. There is no way that they can go to sleep in 20 minutes, or I think there hasn't been any occasion that they are not.
It was your question if the material is so complex that they're not getting it?
If the material is complex, you have to break it into simple things, and there is always a way. It's a matter of engineering to do that. It's not easy, but there is always a simple way. Like Einstein's theory of relativity. It says if you go fast, time dies. Your clock starts to go slow. That's the thing that's so simple. It's a fact of nature, right? Or to make it short. Yes.
I just want to make a comment. In both segments, I noticed that you displayed an image of some sort,
Yes.
which for some people it brings out a curiosity.
Yes.
When is he going to explain it? And so on. So I found that as a very good strategy. And secondly, you spoke very slowly but clearly instead of few words. And I think when you fit that all in that.
So you're rather than something you're coming.
Exactly.
Thank you. Well,
So you took advantage of some of the stuff.
well, I did try.
Alice and Bob situation again,
Well,
created curiosity.
It took us about a week to create, and we have the addresses there, to learn some of these things. And you can always complete that.
I'm going to make a comment to your question, and one of the things that Logan is he was always asking questions as he was going through, and if you notice that your audience is not picking up and not able to answer questions, you have a chance to go back and research. But I haven't explained this well. There's something in the explanation that hasn't gone well. Where if you just like wait till the end of the quarter and do a test, you have no time to research. So
that's what I want. I'm not with this. I'm a good cooker. But I go back and make it better.
That's really good, because how many of us have delivered a lecture and at the end we say, okay, are there any questions? And nobody raises.
Nobody raises. No, that's true. And then the number of tests you put in. And you can measure the case for yourself in case.
Yeah. Do you review the next time you meet? Do you review?
Yes, always. Always. Because like when we started the lecture at Jonathan Landy, you have to have this in your record. That's why you ask, right? This was done before that. So everything about estimating.
Another comment here, building on what you said in the next question, as I was learning about SDL, scenario-based learning, one of the principles is they call them mini lectures. But also reject the concept of just-in-time learning. Yeah. So you give a mini lecture and you get them going on that. I mean, you see where the problem is. And you say, okay, let's get together again. We give another mini lecture. Yeah. And that's and then you let them go back to it.
On our hands-on lab system, we usually don't tell them about the results or don't discuss the results in advance.
They call it in-line process.
Let them do that now. Then say,
I'd like to interject. I'm a big proponent of performance-based education. And I would just give I used to teach technology, I just give them a project to work on and enough information to get started and let them go.
yeah,
And then,
exactly.
and then
Right.
as the questions came up, that's when you fix the
So can I ask a question about that? Because there's a lot of students who want step-by-step instruction, and I'm rethinking that because I don't think they're learning critical thinking if you give them, we teach more like,
Well, that's why it's best to give them the project, you know, and the project can be different things
Yes.
to begin with.
We have all kinds of students. Usually the definition, when they say that Mo is more worried about the students teaching themselves than he's teaching them. And it is true. I try to hide myself, not hide, but like the nature itself, right? I don't give them the results immediately. And so then we go through these questions, and sometimes they go different ways. They're very interesting. Yes, sir.
Do you do your project in team?
Yes. Yeah. Team of 2 to 3. 4 is too much. And they copy each other and team of 2 is not still the ideal. Team of 3 is better. I know. They're all different
I
kinds.
always use 3 or 5, it always helps to have an odd number and people
That's
agree.
3 has been the best number. Thank you very much.
Yeah,